Watch how quickly this dark ink spreads through the clear water. This illustrates the central dilemma for large enterprises today. They urgently need the analytical capabilities of artificial intelligence, but feeding a public AI model requires them to upload highly sensitive information. Once a single drop of proprietary data enters a public ecosystem, it disperses. It becomes impossible to contain or retrieve. The alternative to that exposure is building an internal, isolated intelligence system, a concept known as AI data sovereignty. Because this requires severe organizational and technical commitments, the decision cannot originate in the IT department. The mandate has to come directly from the board of directors and the highest executive levels to ensure company-wide compliance. This grid on screen maps out exactly how that mandate becomes human organization. It's called a RACI matrix. By assigning who is responsible, accountable, consulted, and informed, the enterprise slots its executives and engineers into strict decision-making zones. Everyone knows exactly who authorizes data access and who builds the guardrails. As the grid fades into the background, we see compliance filters drop over an abstract flow of data. This represents the next mandatory phase, a comprehensive regulatory inventory. Before any engineering begins, the legal team maps out exactly which local, national, and industry-specific privacy laws govern the company's information. Hitting those filters forces a hard split. The regulatory inventory dictates a rigid data classification process. All company information is sorted into strict categories of sensitivity, typically flowing into pipelines for public use, internal use, and highly restricted access. Establishing these roles and legal boundaries provides the exact specifications the engineering teams need. The legal constraints dictate the physical shape of the hardware architecture. Leaving the boardroom and entering the server room, those governance rules translate into a strict isolation architecture. The system must physically sever ties with the outside world. This requires precise hardware planning. The enterprise calculates the exact number of local GPUs needed to process the AI workload internally. They also install hardware security modules, or HSMs, specialized physical safes designed to generate and protect cryptographic keys locally without relying on external cloud providers. This network schematic highlights a component called a data diode. It acts as a physical security checkpoint. Notice how the traffic only flows one way. The diode permits data to travel inward into the secure zone, but its physical design blocks any outgoing data pulses from ever leaving. Zooming out from the diode, you see the entire secure zone as a self-contained bubble, completely severed from the external cloud. This air-gapped environment creates a massive operational challenge. The engineers are entirely cut off from the public internet and standard cloud-based developer tools. Those new geometric blocks assembling inside the bubble show how the team solves this. They stand up an entirely localized offline software supply chain. They build internal versions of package repositories, like PyPy for Python code, and proprietary model registries to store their AI frameworks without pinging an outside server. Achieving physical isolation dictates that the enterprise meticulously rebuilds the entire software development environment from scratch, safely within its own walls. With the isolated fortress operational, the engineers can finally begin importing the classified enterprise data into the secure environment to train the system. Even inside the air-gapped secure zone, the raw data must go through a mandatory de-identification process. Algorithms scrub the datasets, stripping away all personally identifiable information, like names, addresses, or account numbers, before it ever touches the AI. On screen is a massive neural network sphere representing a generic foundational AI model. That smaller module snapping onto the side represents a technique called LoRA, or low-rank adaptation. Instead of retraining the entire massive core structure from scratch, LoRA efficiently adjusts a tiny fraction of the parameters, tuning the output specifically to the enterprise's private data using minimal computing power. As the model fragments and distributes across these distinct nodes, we are seeing a process like FSDP, or fully sharded data parallel, in action. This technique takes the heavy training workload and spreads it evenly across the isolated GPUs, speeding up the localized fine-tuning process. Once the tuning finishes, the inference deployment phase begins. The newly customized model connects to an internal API gateway and local routing tools, allowing authorized employees to securely query the AI from their workstations. Through isolated hardware and localized fine-tuning, a generic publicly available base model becomes a highly specialized intelligence engine, entirely owned and operated by the enterprise. The engineering phase is complete, but the sovereign AI does not immediately go live. The entire system pauses for a final, critical validation gauntlet. Before general employees get access, the system must pass 3 severe tests. Security teams conduct penetration testing to find any vulnerabilities in the air gap. Legal teams run compliance validation to ensure the data pipelines adhere to the initial regulatory inventory. Finally, engineers run performance benchmarking to guarantee the system responds quickly under heavy internal traffic. The results of these 3 tests form the final sign-off package. This package is presented directly to the stakeholders for formal acceptance. This exact moment of stakeholder sign-off closes the governance loop. The executive mandate from Step 1 is answered by documented, verified engineering. This massive vault door sliding shut captures the official launch. The system goes live, granting the enterprise an advanced intelligence capability that answers to no one but them, held entirely within their own secure perimeter. The project launch immediately transitions into a permanent maintenance lifecycle. The isolated systems require daily operational monitoring, offline monthly model updates via the localized supply chain, and rigorous quarterly security audits to maintain the integrity of the air gap. AI data sovereignty requires physical infrastructure, strict legal mapping, and entirely localized workflows. It is a permanent, continuously defended operational commitment.